In this quick example video, I'm just going to be using this piecewise function. It was actually on your last exam. And we are going to just use this and not a graph in order to determine if this function f of t is continuous at certain t values in this case, not x. So at certain points, we're going to determine the continuity or discontinuity of our function. If you have not already watched part 1, continuity at a point, please do so because I will be assuming that you already know the 3-step checklist for continuity at a point. All right, the first value that we're going to be checking out is t equals -10. We want to know if we're continuous there. And so our first step in our checklist is going to be finding the function value when we plug in -10. All right, when we plug in -10, that's the exact y value or output, f of t value, when we plug in -10, therefore we're looking at this top piece. So when we plug in -10, we'll square it, right? We'll get 100, and then minus -50, so that'll end up giving us positive 150. So that's defined, so we're good with the first part. Our second part of our checklist is the limit as t approaches -10 of f of t. Now, -10 is a breaking point or change point, however you want to call it, of this piecewise. The other breaking or change point is at -2. We call those breaking or change points because that is when our function literally changes the shape, right? This is a quadratic, it's a parabola to the left and including -10. In between -10 and -2, it's a line, and here it's some sort of funky looking rational thing to the right of -2. So it's where our function breaks or changes. And so we do need to make sure we check both the left and right-sided limits at -10. All right, as we approach -10 from the left, we are looking up here and we're plugging in -10. We already did that, so that is 150. As we're approaching -10 from the right, we need to look here because these are values that are larger than -10 or approaching it from the right. If we plug in -10 here, we'll get 9. And so even though both of our one-sided limits exist, our overall limit does not exist because they are not equal. So we cannot move on to step 3. Step 3 would be seeing if these two were equal to each other and 150 does not exist. So our function f of t is discontinuous or not continuous when t equals -10 because the limit as t approaches -10 does not exist. So here is our answer. Let's take a look at the other changing spot at -2. All right, if we want to see if f of t is continuous at t equals -2, the first thing on our continuity at a point checklist is finding the function value at that point. So f of -2, we would have to plug in down here because that is when our function can equal -2. And if we cube -2, we'll get -8. And when we plug it in down here, we'll get 7, so -8/7. The second part of our continuity at a point checklist is the limit as t approaches -2 of our function. And again, we have to check both the left and right-sided limits. I'm just going to, for the sake of time, write L and R. I hope that's okay. As we approach -2 from the left, we're looking here. And so when we plug in -2 as we approach it from the left, we'll get 17. And as we approach -2 from the right on our function, we're plugging it in down here. From the right is values greater than -2. We already plugged that in. It's this funky fraction, -8/7. Therefore, our limit does not exist. And therefore, our function is again discontinuous at this breaking point because of the same reason that the limit does not exist. Now, is all hope lost with piecewise functions? No. Let's look at this last example for some positivity and seeing where we can be continuous at a breaking point in a piecewise function. Let's take a look at this piecewise function f of x. It does have 4 pieces, totally cool. Our breaking points would be 0, 1, and 3, and so if we were asked to evaluate, or not evaluate, but if we're asked to look at those points, we definitely have to make sure we're looking from both the left and the right. So let's pick one of those 3 breaking points, x equals 1. Again, we want to know if we're continuous there. So our first step on our continuity at a point checklist would be to plug in 1 to find f of 1. And we'd have to look here. And so we'll have negative and then 1 squared. The negative does not go in the parentheses, plus 4 times 1, and then minus 2. I'm writing this all out because of the PEMDAS can be confusing. So I square 1 and then multiply by that negative out front. And so we'll have 3 minus 2, which is 1. Interesting. So f of 1 is 1. Cool. All right, the next thing that we want to look at is the limit as x goes to 1 of our function. And we do have to look at the left and the right since it's a breaking point. All right, if we look at the limit from the left, we need to look up here as we approach 1 from the left, and whatever we plug in, it is that value. So our limit from the left is 1. And then as we approach x equals 1 from the right, we plug it in here, which we already did, and we know that that output is 1. So our one-sided limits both exist and are the same value. Therefore, our overall limit is 1. So our function's defined at 1. Our limit exists at 1. The third step in our checklist for continuity at a point is, does our function value and our limit equal the same thing? Yes, that works. So is f, oops, I just hit pause. So is f of x continuous at x equals 1? Yes. Let's write out why. We will say yes because f of 1 exists, or is defined rather, and it equals the limit as x goes to 1 of our function, and they both equal the output of 1. So this is implying that f of 1 is defined. This is implying that the limit exists, and this equals are showing that they're equal and they equal 1. So there is possibility that at a breaking point in a piecewise function we are still continuous.